as we talked on last week, today I will start the class on organic semiconductors, but my focus will be on semiconductor in general, but they can also be applied to semi-metals properties. So I will start with the materials properties, how the organics can conduct, and what is necessary to understand the transport. So after our class today, I would like to ask, I don't know if there's anyone online here. Not yet, but they can come. But after our talk, I would like to ask the talks that you both think that could be more interesting for your experiments and also for the improving of your research in terms of organics. So I also planning, actually I reduced it to talk about the talks that I proposed in the beginning, but to have this spare time so we can discuss more, I will reduce they do 2 days together, so we have more spare time to discuss regarding the benefit of this course for your research and how we can do on the lab, for instance. So I would so for this, I would like to both of you give me feedbacks on the to understand how exactly are you guys working with. For instance, I know that you are working with self-assembled monolayers, right? Organic self-assembled monolayers for whole transport material, and you are planning to apply for perovskites, yes. Right? Yes. Okay, so I can type. Both of you are with self-assembled monolayers. Mm-hmm. Yeah. Okay, just to be clear, because we have a lot of whole transport layers also, so I can focus on just the self-assembled monolayers and include this on the next classes and the discussion regarding the techniques that we can use. I will exhibit the techniques that we have available in the lab. Also discuss the techniques that can have here nearby or with some multi-usual laboratory. So I will start in this topic for this focus, focusing on your specific research. So I think it would be better for both of you. So to start, as we finished last class on the transistors, so the optical, the transistors, and also the devices, optoelectronic devices. So I just gave overview on how it works. Now we are moving to how disorderly. So in terms of ordering, organics are more disordered material, and how they through disordering create the electronic structures that we can apply for optical devices or electric devices, and how we can also manage the charge transport in these materials. So here I will show some specific model So we can use in physics one model that is very interesting to use and see the correlation with the model, with the experiments. And then also how these two topics will be on the next week, but how the materials that organic materials can be related to these devices that we discussed on this, and the degradation and characterization pathways to understand the organic materials, right? So in this topic, we will starting for since atomic hybridization. So how the hybridization of carbon can be the main influence to the electronic properties. So if you are working with organics, you can you know that carbon can be hybridated their orbitals with 3 different hybridization. So our electrical behavior, they goes to the sp2 hybridization, and also in terms of organic, we know that organic is more amorphous than inorganic materials. So in terms of electronic properties, if you think that the electronic structure always came from the crystalline structure, how it could be working with organics if they don't have a periodic lattice. So in terms of disordering, this material, they behave more like disordered driven electronic instead of ordering as inorganic. So this is the beauty behind organics, because you think around the disordering, you think that is not good for materials, but in terms of organics, this can give the electronic properties and also all the technologies that we can apply these organics on the electronics devices. So here, I don't know if you want to. I also can send the slides for you both. I didn't send, I think, the last one, but I can also send this. Here, there is a few examples of organic semiconductors. So in terms of tetracene, so means that we have just carbon and hydrogen here, and they are bonding with this sp2 hybridization. Chlorotetracene, pentacene, tips pentacene, P3HT, 6-thiophene, alpha 6-thiophene. So in terms of the, for instance, P3HT is polyhexatylthiophene. So this is a polymer, this is small molecule. This is also a small molecule. This is a porphyrin, phthalocyanine, and a rubrin. That is a small molecule also. But what they have in common is they have this sp2 hybridization, because we can see that they have this dupla bonding on the carbon, and you know that inside of benzene you can share this this bonding with the near carbon here. So it means that your bonding, the second bonding here, it's delocalized over all the carbons. So this delocalization will give some structures similar to valence and the conduction band of inorganics. The same we can see with these structures. So we have here also the sp2 hybridization. This is fullerene. This is the fullerene with this alkyl side chain to improve solubility. This is also a small molecule. This is small molecule. These another two are examples of small molecule, but what they are different each other. We can see in terms of electronic structures and also the chemical structure, that in this side there is more oxygen, fluo materials, so they have this internal charge transfer. So in terms of electronic structures, they can be acting as a acceptor of the electrons, and this one, they act as donor of electrons. So in terms of organic photovoltaic, for instance, as we mix the donor and acceptor, so we must mix two of them to have the absorption of light and also the extraction of the charge. So this is the one of examples. We also have materials that can be acting as just conducting layers, or also blocking layers as ATL or hole transfer, HTL or ETL. So in terms of structure, they have this similar also structure, because they to organic be applied in electronic devices, they need this conjugation inside the organic compounds. So this is the main rule for organic electronic transporting. So they fundamentally distinct from the inorganic crystalline materials, because they emerge from molecular orbitals greater than periodic bond structures. So how the carbon created these two orbitals that can be splitting into the energy of the visible light, we will discuss in the next topic. But we saw that in organic semiconductors, inorganic semiconductors, we have this strong covalent bonding that could extend the electronic states. So if you have the periodicity, let's see, a more continuous, stable, you have the better electronic structure. But in organic, we have these electronic properties related to the p conjugated molecules. So it means that we have the p bonding, which means this second binding of the carbon, and this bonding is delocalized over the carbons, but they need this molecular arrangement. It means that depending of the morphology of your material, you have a more favorable to transport or not. So we will see it today. So how we can relate this electronic transport in a system that do not have any longer range periodicity. So in terms of hybridization, just to remember, I know that you are chemistry, so maybe you already saw it, but there is another people that has different backgrounds. In terms of carbon, they can split they can do hybridization of sp, sp2 or sp3. So in terms of sp2, that means we can type the orbital s with 2 orbital p, so they have the same energy. And when we approach the 2 carbons with 2 hybridization of sp2, they bonding will be sigma bond between this region of the to tighten the molecular behavior of the material. So this p bond will be related with the carbon structure itself. And we also have another a free sp2 bond here. And with low energy, we have this pz orbital, because in terms of energy, you take sp2, so Vx, Pi, and with low energy, Pz. So the carbon has this Pz sparing orbital that has low energy. So in terms of electron, they will feel during the bonding each orbital, each sp2 orbital. And sorry, I will finish here the bonding. And in terms of p bond, should be the pz orbital that is perpendicular to the plane of covalent bond here. So we have this p orbital. You know that every orbital has their shape. In terms of s is a spherical shape. P has this S. S has this spherical. P has this balloon-like the shape. And when they hybridize it, they do like true hybridization of the orbital. So in terms, if you see the cross section here, just for curiosity, you see spherical, but they also have this balloon shape. And the p orbital is perpendicular, so it means that they have this balloon more spread. And to share the green electron that are just right here, they can share just in terms of perpendicular bond. So we call it p bond. And the p bond has this weak bond, because we can, if you see in terms of orbital, here it's quite hard to break. So this we can break easily we using dipole, some electrical field, or some also contaminant, oxygen, for instance, we can break this bonding and do the contact with the carbon with the oxygen, for instance. That is one way to degrade the electronic properties, because if you lose this bond, you lose the electronic property of your material. So the P bond is the main responsible for the electronic properties of organic materials. So here you have two carbons, two atoms. If you have this polymer, for instance, that you have several carbons that they can share the electron with each other, they have several p bond here, and they also can spread this bonding over the carbons that has this sigma bond. So in terms of information, I think I said everything. So in terms of unfortunately, when I transfer from my computer, they just go over the information. But in terms of what model we need to use to explain this behavior, we use a molecular model, molecular orbital theory. So we can, using it, we can find the highest probability to find electron in a molecule. So this comes from the shape of the orbitals, and they also have the singlet and triplet orbitals. So it means that we have some rules that we must fill in terms of electrons distribution because of the orbitals allowance. So the molecular orbital, when we do the binding, it arises from the atomic orbitals itself. So in terms of energy, we can see, for instance, I just gave here what is the molecular orbital theory. In terms of energy, for instance, if you have two electrons from the carbon, they have this wavelength and the wave function of the electrons. So we have a combination that is constructive, which means that we tight the molecule, or we do this bonding, and this wave function where we have this constructive interference, we have what we say as constructive, and we call it as bonding state. So we have the constructivity interference, we have the bonding orbital sigma, and also the orbital p, for instance. This is the lowest energy for electrons. So what I'm saying is, if you have, for instance, here one electron coming from the carbon, we can see that is one sp2, for instance, and this is the carbon, second carbon, sp2, with this one. So we must share the electron with each other. So what they do, they split the energy into bonding and to anti-bonding state. So in terms of sp2, this is sigma bonding, this is sigma asterisk anti-bonding state. So their electrons will go to bonding state with Fermi rules be allowed because we do not have the same spin with the same quantum number. So we have these orbitals. Here are the atomic orbitals, and here are the molecular orbital, which comes from the atomic orbital isolated. So we created this sigma and also the bonding and anti-bonding states. So we have this PZ state that we can have high energy, PZ, low energy, sorry, and PZ here. And also they have this, I didn't draw it with perfect scale because it should be with this energy, the P. So this is the P and anti-bonding P here. So unfortunately I draw it wrong, but I put it on this slide also. So we have this bonding here having this molecular orbital inside of the atomic, depending of the atomic interaction. So we call the constructive interference the lowest energy of the molecular orbital, and destructive interference the highest energy of molecular orbital. So in terms of orbital itself, I just put here for instance, one s orbital. When we have this constructive interference, we can see that the electron, they can share the same electron with each other, and they have this bonding density being close. So when they have this anti-bonding, so they have destructive interference, and they have some free space between the orbitals, so they interact like they cannot, their distance are too far, so they break the bond. So in terms of energy, to go to this orbital, it's quite high energy. To go to here I put to go to the sigma anti-bond orbital of the carbon sp2 hybridizated, it's quite high energy. You can do it use a synchrotron light, for instance, with high energy. You can break this, or you can use X-ray to break the energy of electron to promote this one, or to do Auger also electron from the carbon. But if you do you promote the electron to higher energy than sigma orbital, you just break the structure, and you don't want to do it. But sometimes you can do it in your material. And if you see the p bond, you can see that the p bond in terms of energy, bond and anti-bond energy, they have the bond and anti-bond with low energy than the sigma. And this energy, this quantity of the energy is inside of visible light. So this is the reason that why we used the carbon's p bond to electronics devices. So when you see here the electron with spin up, spin down, you can promote this electron to the p antibond orbital just using optical excitation. So if you want, for instance, to create organic solar cells, you can use this material to absorb the light, promote the electron to p antibonding orbital, and this electron you must catch before they recombine, but you can do it because this difference in the energy is inside of optical excitation. So it's in the visible light. Here we discussed it regarding just the bond of two carbons and what happens if we have several carbons. So we created several steps, several states with the p states and also antibonding states. And here we have the sp2, they have the sigma molecular bond and sigma antibond state. So you saw here, you can see that is high energy, here is low energy, and you have several carbons, you have several states, and we can call HOMO the highest occupied molecular orbital. So it means that the highest orbital that has electron in the system. And LUMO is the lowest unoccupied molecular orbital. So this is the lowest in terms of the energy molecular orbital that has not any electron. So you can see in terms of inorganic that the HOMO can be related to the energy of valence, and the LUMO can be related to the energy of conduction bond, but they don't have bond. They just can be analogous with the inorganics. But if you have here you just have the benzene. If you have more benzene here, you can think that you have more steps. And if you have a polymer, so you have even more carbons with sigma p bond. So we have these n states that can be available to the electrons be occupied or unoccupied. So if you use light, you can promote this electron from here to here. If you use electrical field, you can inject electron here and recombine emit light. So it's already. If you just use field, electrical field, you can move this electron, so you can create one transistor, and also further you can manage these states with the dipoles. For instance, if you approximate one molecule, for instance, carbon dioxide, you can, using this dipole from the carbon dioxide, to create inside the electrical field, and also bond this electrical, so do with the organics on sensor of carbon dioxide. So the properties of the carbon semiconductors, they can be applied to several things and to several technologies. And every technology, they rely on the disordering, that is this number of states that we created and can be managed inside of the material. So in terms of orbitals, neighboring molecules, here we have the benzene that is rigid. If you think that you have another benzene with a sigma bond here, you can rotate the molecule, and the rotation of the molecule also created the new states inside of the gap of energy that you have. So as analogo, we have this difference in HOMO and LUMO, and this difference in energy we call energy gap for organics. So if you are measuring, for instance, your organic, and you want to measure the energy gap, depending of how molecular are organized the carbons, or how the morphology of the carbon are organized, you can have different values of energy gap because of this distribution of the carbon's free states. So the transport, they do not rely just on energy level as inorganics, but also in overlap of wave function between the molecules. So if they have this overlapping in the wave function, we can share this electron inside the material, so transport it easily. Just to remind the wave function overlapping and the transfer of the state, we have this initial and final state, and the transfer state that we manage in terms of quantum mechanics, we use the Hamiltonian to see how we can promote the transferation of the electron from the state of final initial and final states. And if we have the large overlap between these two wave functions, we have a really good transport. And if we don't have the overlap of the overlap is small, actually, we have localized states. So the transport between states can be happening through hopping. So this is the characteristic of the organics, because sometimes the orbitals then cannot be overlapping. So we have some free orbital here, and then depending of the energy of them and the distance, of course, we can hop between the states the electron. So the transport of the organics is not just through the through the overlapping of the states, but also through the hopping between electronic structures. I also feeling sometimes it is too hot, but sometimes it's cold. I don't know what I can do anymore.
It's going hot. Sometimes we have a lot of sunny, but sometimes it's really a lot and it's really a lot and cold.
Last week I was walking, suddenly was dropping ice, from this, not yes, I forgot ice. Snow. It's not snow, but it's hard rockets. So it suddenly really have a rocket, even hurt. It's quite messy this weather. So in terms of transport, the electronic transport of organics, they do in different ways. If they have this organization, they can do this, but in general, the main characteristics of the organics are the transport through the hopping between the states. So, as I said, the electronic coupling, which means the overlap between the states, is sensitive to the intermolecular distance. Also, if they have face-on or edge-on orientation, if they are this way or this way, they have different overlapping. And also the PP stacking alignment. So what I want to say that small in organics is fundamental, that small structural variation, you can have this exponential change in transport properties. So as I said, when we have this coupling, when we have this overlap between states, we can delocalize the electron over the material. And if we don't have this coupling, we localize, but we don't have this coupling. Actually, we have a small coupling, but we needed to have at least one part of coupling. And if you have this small coupling between these states, we say that the states are more localized. So it means that we have localized carriers tight inside the organic materials. So we have this competition between the electronic coupling and the disordering. So the electronic can be related with this T, and if the T is high, we can say that the transport, they like more like bond as inorganic. And if the overlapping between the states too low, we can see that the transport is ruled through hopping. But in general, we use this second because it's quite hard to have a very perfect aligned organic material. So in terms of electronic properties, we need to introduce what is the localization length. So which means is the length where the carrier are localized. So we call localization length in terms of we have this quasi-particle created there, and they not recombine, and or they can be recombined inside of this length. So this length is the length that they have before be recombining. So as we said, the strong coupling extend states, and the strong disorder, that means the opposite of the coupling, we have this localized state. So in terms of, I got this recent paper to show what it means in terms of it. If we have this amorphic structure here, sometimes we can see some region that can be more regular. So here they just said they just put this molecular with electrical field, and the carrier are delocalized over this messy morphology, are localized and doing hopping between the states. But when they have this morphology, more continuous morphology here, they also have carriers that can be localized with this length. So in terms of length, if you see the amorphous, the length will be lower than with this region. And you also can increase the localization, which means that you increase the delocalization of wave function. So you have more, your morphology are more crystalline-like. So you can stand the structure here. And if you have, for instance, the applied electrical field, they can accumulate in this bonding here, grain boundary between the totally amorphous or some non-amorphous region of the polymer. So in terms of the electronic properties, sometimes you want this, but sometimes you don't want this morphology because they will match with your disordering between inside of the amorphous structure. Carriers are often localized on a few molecules. So here was one example. And if you think we just discussed regarding the electronic properties, the carbons material, they have this really dynamic disorder. So which means that you have a more free, liberty of the molecule to do some specific movements, for instance, rotation or translation between the nucleo. So we have this behavior of the electronic structure. If you think in two atom system, when they are, we can do the diagram of energy rotation of the two atoms with one electron, for instance, just to simplify the model. So if they are bound, so they have this lowest energy. If you have decreased the intermolecular distance, you can decrease, but the energy will be even high because you have this limitation of the radius of the electron of the atom. And if you increase the distance between the electrons, the atoms, the nucleo of the atoms, you can suddenly break the bond. And this is the potential that you have. But inside of energy nidpotation, depending of the number of molecules that are involved, you can have some vibration states with the steps are given inside of the energy potential of the molecule. So this means, in terms of carbons, that you have in organic materials more vibration because you have this disordering. So you have more free, I forgot the word, but freedom, more freedom to move. For instance, stirring the carbons or pushing several vibration that they have rotation, and also this can be related to the thermal fluctuations. So in terms of comparing organics and inorganics, a small variation of the temperature is quite important to the electronic properties compared to inorganics. So it means that when we are seeing the transport of the organic materials, we must analyze it in terms of time, because if you move, for instance, you apply one electrical field, you move the morphology, and if the morphology moves, so we'll create a temperature. The temperature increase, so it will give more freedom to the morphology be changing. So this is quite challenging because you must to analyze it in terms of the temperature, all the transport that you have in your material, because of these dynamic fluctuations. So just remind we need to have strong coupling or low disorder to have this bond transport and the static lattice. And in organics, we have everything in the opposite. We have weak coupling, strong disorder, and also these dynamic fluctuations. So I put here, not yet, actually, it's there. But here is what I'm saying regarding the localized states. We have this transport being through hopping between localized states. So you can move the electron to the nearest in terms of the energy, but they not totally overlapped. So it means that we have this hopping between the states. This hopping, they can happen in terms of polymers or also small molecules, intrachain or intramolecular hopping, or interchain hopping if they have a polymer structure. They can also do hopping between anions. So the self-assembled monolayer, they have these anions to tighten on the substrate and to tighten your next layer over your self-assembled monolayer. So the transport is also influenced using anions or cation-strapped transportations. So what I want to highlight here is a small variation in your system, and they will affect really hard on the electronic properties of the material. So the random energy landscape is like this, that they can be related to the density of states of the material. And the transport, as we are already discussing, they can be happening through the percolation of the states. So we have this hopping between the states. And in terms of the energy distribution, we have the free available states here, and they behave like a Gaussian distribution. So every organic material, they don't have the specific state as inorganic, but they have this Gaussian distribution. And also we can have on the end of the distribution some trapped charges, which means that they, even with a small temperature, they can, or high temperature, they cannot be released. So they are really deep traps in your material, and these are inside of the Gaussian that you have. So sometimes you cannot distinguish if they have free states. So to do it, you must analyze in terms of temperature if you want to see the charge transport properties of the material. So just to highlight in terms of, I will give more information on it when we do the measurements. But if you see, for instance, this molecular disorder, dynamic disorder, you can do the absorption measurement, and the absorption measurement will give you a peak, and this peak is not a specific peak as inorganic. This is one example, but you have this broad peak because of the molecular rearrangement, and also the vibrational states that are available to your electron. So here are also one example with the photoluminescence. So you don't have sharp peak, but you have this a large peak with Gaussian behavior. So if you analyze just the shape of the peak, you can have more information on your morphology and also the electronic coupling between the morphology and the electron. So the distribution that is ruled, the disordering of organics. And if you think, when you use the material close to a metal, as we discussed in junctions, so they have these several free states that can be transporting through the hopping of inside of the organic materials. And metals has these very well defined states. So when applying electrical field, they can feel the organic states. They can also, through the feeling, move the electronic distribution. So it's quite dynamic. It's not totally static. So you, when you also do the measurement, or you also applying devices, you must be careful because of this dynamics. But in terms of advantage, it means that we needed just, there is no too high difference energy between the states. So a small energy, you can feel this state. Okay, so we discussed it a bit. If you have questions, also you can ask or interrupt me. It's not a problem. But we discussed on organic how they can transport, and we don't discuss it regarding all the orders, how they are created in terms of energetic disordering. So the disordering, as I said, they can be related to the morphology organization, but this morphology organization, they can vary. If we have dipolar fields can be done using another atom nearby or molecule. They also can do conformational change using, for instance, difference in the temperature, or also if you are doing deposition with one specific solvent and you change the solvent, it's totally different because one solvent has dielectrical constant different from the another solvent. So it will both influence on dipolar fields or conformational chains. And this will impact in the performance. And if you see here, for instance, I got this paper. They did the AFM, AFM measurement. Are you familiar with AFM? Atomic force microscopy? No, you'll never use it. Okay. I will give more talk regarding AFM on the next class. But AFM, they can see in terms of interaction between the tip of the equipment with the surface of your sample. You can see how in terms of electrical interaction between the tip, how the atoms of the surface are organized. So we usually use, I was thinking also to say to you to prove how you deposit over your substrate, your material. You can use the AFM because you can see if the morphology is changing. If you see, for instance, here they used pentacene. So this is topography image. So it means that with the brightest, it's high level in terms of 3D, you can see here, but has this roughness and this dark region. They have this small region of the surface. So AFM gives this information regarding on topography. So you can see, as you see in scanning electron microscopy, but scanning electron microscopy are not as suitable to see films, organic films over the substrate. So for this, it would be better to see through the atomic force microscopy. And AFM, they can also, through the tip and sample, apply electrical field. So it's called Kelvin probe, a Kelvin probe microscopy, where you can see this difference between the energy of tip and the surface, and you can relate that, for instance, Here you have more negative, which means that you are attracting your tip. So this could be related to one material, and this one can be related to another material. So you can distinguish your material, and if you have some standard, you can correlate it to your new sample. I don't know if I spoke it properly, but AFM is one of the best techniques to apply for organics, and I know that they have now here downstairs. I don't know if you already saw the microscope, but it's downstairs. Us here, they have the AFM microscopy. So just to show how the solvent really influence on the morphology properties, this is not the solubility of the material. In this case, they just did the film and put the solvent as a vapor annealing solvent to modify the surface of organic film. So in terms of to continue the discussion, here I just said regarding the origin of disordering. And if we have this localization of charge carriers, if we have disordering, we can shift between for instance, if in the morphology here, you can shift between the states through hoping, but you know that in organics we have these very well localized carriers, and it's quite important to mention that we don't have electrons and holes free in the material as in inorganic. So we have formation of polarons, which means that they have this they are quasi-particles formation between the electron and the morphology of the organics. So because they have these very well localized states, they influence they have very high influence on the morphology of the material. So they created this quasi-particle polaron. So what is the polaron? Is a charge carrier, electron or hole, coupled to the lattice distortion. So you have this, I didn't have any figure to show, but it means that you don't have free electron inside organics, and but you have the electron or hole tight with the distortion of the lattice. We can correlate it to electron phonon coupling in the organics. So in terms of polarons, what is polaron? When the charge moves through the material, you can see that it interacts with the surrounding molecules. So if you think regarding the states that I showed the slides. So here, the free states randomly created because of the molecular interaction. The electron here can hope between the states, but they they don't move without create some reorganization in the morphology of your neighborhoods. So it means that you change the state, you change the morphology. So this is the polaron because we cannot say that they are free to move, but they are tight in the molecules. We have, just for curiosity, two kind of polarons, small polaron and large polaron. So for organics, we have small polarons because they have this strong electron phonocoupling. And if they have this weak electron phonocoupling, they can be called as large polar. Okay, so the modeling that I was talking, how we can know and also understand how the transportation are done inside the organic materials. We use this transport mechanism through hopping between the states. So we have the hopping through thermal assisted hopping. And also we needed to know how is the energy landscape or how is the free states available of your material. So in terms of hopping, we have these states that are already rotated there, and these states, they can be discovered using density of states, and to do this the transport, there is several kind of models that I also will discuss, but we generally see the relationship with the energy available states and also the temperature, independently of the model that they are used to simplify the transport of organics. One example of modeling of theory is Marcus theory. So Marcus theory in organics, as we discussed, the charge transport occurs between localized molecular states and not band. So in terms of Marcus theory, we have this transport ruled through charge transfer between molecules. So we have this charge transfer reaction between one initial and one final molecule rather than continuous motion. And Marcus theory, it's quite curiosity, but we can do this model to use quantitatively to process quantitatively the quantitatively properties, and also the result of using this model, this theory, are very well related to experiments. So this is one of the most famous modeling transport for organics. And what the Marx theory suggests, first we need to this parabola. It's parabola in English. I don't know if you know when I say parabola, parabolic, okay. Sorry, because sometimes mess my head regarding Portuguese, French. So parabolic states are the states of the electron that they have, as we discussed it, because of the bonding between the atoms. So in terms of Marcus theory, we can see that the initial and final state, they are localized in one molecule A, and the final state in a molecule B. So this is just the figure, initial state and final state. So this parabolic configuration, they come from the molecular orbitals. So we need to know the morphology, also the organization of the atoms of your material, to see how electronic are distributed inside the parabolic shape of the energy dispersion. But as we discussed, when we shift one electron from the initial state to the final state, we have this reorganization on morphology because of the coupling between the electron and the surrounding of the material. So we call this lambda is the reorganization energy, is the energy of the molecule to reorganize in the system. So if you see in terms of this true parabolic system, the initial state and final state is the difference between the lowest energy of the initial state with the energy correspondent to the lowest energy of the final state. So when you see the parabolic structure, the lowest point means that is the distance, intermolecular distance with minimal energy. So here in the initial state, you have the minimal energy here, and you have the minimal energy here. And here is the energy correspondent in the initial state that has the same molecular distance. So you see this reorganization. If you think in terms of molecular vibration, if you vibrate your molecule, you can stir or you can push or something, but you move the distance between the nucleus. So if you have the lowest in terms of the temperature, you can have this organization. And when you promote the electron to the other side, this will move the configuration. You can, for instance, you will have this large separation. So to compare, the model proposed that to see this transfer, you must choose to correlate the energy of the same state with the same the energy of different state with the same configuration, and correlated with the difference in energy of the lowest energy of the state. So it is the molecular distance. You need to know these two parameters. So the lambda is the energy carried to rearrange. So they are related to molecular geometry, also surrounding the environment. And you can think regarding transport, if you have high lambda, you have one configuration that's harder to transport because you can be so difficult to reach this state. And if you have this low lambda, it could be easier to transport than too high lambda. But you don't have just this. Don't have the reorganization energy, but you also have the driving force, which are the force related to the difference between the lowest energy of the states. So the driving force are related to the free Gibbs energy of the reaction. So you can compare this free energy in terms of thermodynamics reaction with the electronic transport. So using Marcos' equation that he proposed, the rate to transfer one electron to another state is correlated with this reorganization energy. The driving force or free Gibbs energy that can be obtained through the configuration of final initial states, the temperature, and also prefactor. I wrote it wrong here, but prefactor R A because it's proportional here, where there is several new modeling proposing on new materials, but we can in general see that they are proportional to the V, and these V are related to the orbital overlap, also molecular orientation and PP step. Just for curiosity, but if you have this change in morphology, you have a better or worse transport. In terms of barrier, okay, so just give this talk on here. So we saw, I just get other figure, but it's similar with another one, just to see that there is some specific rules inside the Marcos theory to have this transport. So if you have this reorganization, energy higher than the driving force or the free energy, the Gibbs energy, you have a normal region, or it's favorable to transfer the electron from the initial state or to the final state. And if you have the same energy, it's it will depend of the surrounding, but they usually are not very well. There is not a very well probability to transfer, but it's on limit between the transfer interval. And if you have this energy of the states higher than the energy of reorganization, it's a anomalous region, so you don't have the transfer is not so fast, but they also are not very well defined. So the transfer rate can be related if you have this difference in the energy of the organization. Just for curiosity, this Marcos theory we can, in general nowadays, apply to organic solar cells, but this lambda free gives energy, and also the constant, they fluctuate because of the disorder. So there is inside of Marcos theory new modeling proposing the transportation, and everything that is done is using statistical analysis of the transport. So, for instance, here, one application of the modeling is to analyze it. One application, just put some specific application on donor and acceptor interfaces of organic solar cells. So, if you have here organic solar cells, you must have organic acceptor and organic donor, and you can study the probability to dissociate the exton created in the organic semiconductor using Marcos theory. So you analyze the electron transfer process from the donor to the acceptor, or the reversed whole transfer process from the acceptor to the donor. You can also analyze it in terms of states. We know that electron can, there is some triplet states on the molecules, so we can analyze in terms of transfer to the triplets states. We can also see the charge recombination system between the interfaces, and also between the semiconductor and another interface here that is HTL or ETL. In terms of application on solar cells, it can predict or propose some charge separation more efficient, or reduce or increase the voltage losses because of the recombination pathways here that are minimized, and everything that is proposed through this model, it's applied to organic solar cells. So we don't have just a Marcos theory to explain the transports of organics, but we have several models. Here, I just got in one paper several theories of charge transport. So if you have, for instance, here a single crystal, so inorganic modeling, inorganic material. So we have this bond-like transport, as we discussed. We have the polycrystalline, which means that we can have both acting in the same material as region with regular crystals or region with amorphous, but the disorder are very weak. So we have the mobility edge model, the multi-trap and release model, and also the models that could be applied is variable range hoping because of the polycrystalline structure, and also the bachelor Gaussian disorder model. And in terms of amorphous, which are disordered materials, so we have these two models that I already said, and also the percolation, that is the hoping between the states. And we have the charge transfer or nuclear tunneling, where we can include the Marcus theory inside of these models. So you know that has several models, and inside of models there is several proposed of small modification to analyze with a specific application in a specific material. So just to give an overview, these are the most popular one. So the bond-like transport, as we discussed it in the first class of this course. So we have the transport be dependent of the temperature. We also have this multiple trap and release that can be applied in organic, for instance, where we also have the every transport modeling actually has this relationship with the temperature, but in terms of the region and also in terms of the material, sometimes the mobility or they can be well related to the model. So to investigate, for instance, if you develop new material and you want to see if the properties of transportation, you must to do it in terms of temperature. So analyze the mobility in terms of the temperature, not just in ambient temperature, because a small variation of temperature will impact directly on the charge transport. And we have these another 4 examples: variable range hoping, Bachelor Gaussian disorder model, Marcus theory that we discussed, that they nowadays are the most used for organic polymers, mainly on organic solar cells, and also nuclear tunneling, that it's almost close, but to the charge transfer between the Marcus model. So the key takeaway message with this course, actually, I didn't see that I quickly I say it quickly today, so I finished early. But the main message is organic semiconductor. In organic semiconductors, disorder are not a defect. There's not a defect. It's the governing physics that rule the transport. The disorder can act to degrade the performance on inorganic semiconductors, but in organic semiconductor, the disorder, they define the 3 states for electronic movements, and also they govern the charge transport. So the main duty here in the organics are the correlationship between the ordered region and disordered region that could sometimes rises from the, for instance, if you have one polymer and you apply temperature higher than temperature of Tg of the polymer, so you have some vitral you reach the vitral, I don't know how to say in English, but you have some organization of the polymer because you reached the Tg of the polymer, so it will modify the molecular organization of your material, and sometimes it is not desirable because you need the disorder to have the transportation. So in terms of electronic properties, disorder are better, is better than some molecular ordering that can badly impact the charge transfer. So that's it for today. I think we can discuss it on the next classes. I don't know if I have someone online.
I'm here.
Hi, Luis. Just Luis?
Hi, Professor. Hi. Can you hear me?
Yes, it's just you online. I cannot see anyone here.
Yes, yes. No. It's me and the Kyle.
Okay. So, guys, this weekend we have this summer shift, and I didn't realize actually that I don't know if you saw that the time changing, but I didn't see on Sunday that
on Sunday, on the last Sunday.
So I'm sorry that I didn't say to you guys that the days are in the different time zone.
Yeah.
So I don't know if you got all the class. Luis, can you hear me?
Yes, I can.
Okay. So sorry that because we have this time shifting time zone. So in the next two class, I will talk about some topics that I proposed here. Also, inside of the research that you are doing. So if you girls want to say something that I could organize besides the material. So if you want to, you said regarding the talk plot, the how to get the energy gap of materials. Yeah, I can also discuss on it. If you have any suggestion, Luis, also I would like to know if you have some curiosity for a specific related theme that could be related to the last classes. Some characterization or some devices. I can also focus on this. Go ahead.
No. I'm sorry. I'm sorry. You can continue. I'm sorry.
Okay, no worry. So I will focus on discussing of the you work on solar cells. So I will focus on more on solar cells, also on self-assembled monolayers and perovskites. I didn't said anything regarding the perovskite itself because perovskite it's quite challenging between the inorganic and and the organic if you have this map configuration, but they have some intrinsic behavior that is different from the. I can also focus it on the next class. Caio wants something that I can be done. I don't know if Caio is hearing.
Yes, can you hear me?
Yes, can.
Hi, Louana. So, what you mentioned about the perovskites and organic materials, like that inorganic and organic assembly of materials, that can be interesting because it's something that I'm working on right now with the 2D materials here in Canada. So, maybe if you can talk a little bit about how can we tackle this problem of understanding what is going on between the organic and inorganic layer, that would be nice for sure.
The interfaces of organic and inorganic layers.
Yeah, something like that.
Okay, I can seek on it also to do more because I talked to the girls here in the we will have this true meeting and we have Easter holidays here in France.
Yeah, on Monday.
Oh, this Monday already.
So this week will be 3-day weekend. Saturday, Sunday, and Monday.
Okay, but they have there is also another that they send me. I can also send you, but the academic course will be closed in 2 weeks of the April. You saw it? I think the lab is not a problem, but just the courses, we are not available to do any courses.
So we only have 2 lessons left?
2 lessons left. I will compromise it on 2 lessons because we will have this break in the I don't know, I think in 2 weeks. I will just check in my laptop. But after these 2 weeks, we have this event. I don't know if you are attending the event, the perovskite halogenate event.
The conference?
Yeah, the halogenated perovskite, halogenated perovskite event.
In May?
In May,
So the first week of May.
In the first week, so we have these 2 weeks, the 2 week of break, and then the 1st of May is the event. So I would finish in this day, but as we are going to the event, I will reduce to the just next 2 weeks.